Good day, everyone. Today, we will talk about the current researches in the field of nanoparticles. Nanoparticles are very important in the field of nanotechnology, and thus there is much research about their synthesis and applications. Magnetic particles are an important subset with many potential uses. Biomedicine is a particular field where nanoparticles are of much importance. Magnetic nanoparticles or MNPs have been increasingly researched for their uses in this area. So now, let's talk about the current researches of nanoparticles. The first one is Pankers et al. 2003, reviewed some of the physical properties of magnetic nanoparticles and described some of their biomedical applications. In this research, external magnet is the key to the moving of magnetic particles along the blood vessel. When they arrive at the targeted site, the environment of the site breaks the coating of the nanoparticles and releases the drug. Second one is Alexio et al. 2000. Studied the injection of magnetic particles or ferrofluids to bind anti-cancer agents to a tumor area with magnetic field. The model used in their experiment is rabbits with squamous cell carcinoma. Alexio found that ferrofluid with metosantrone had great effect on transporting anti-cancer drug to the tumor and had the effect of permanent remission of the squamous cell carcinoma compared to a no treatment group. They used starch to coat the drug such that it binds to amine groups of MTX HCl at a pH of 7.4. Another research by Park, Kim, Lim, and Kim 2008 have tested the change in size and saturation magnetization of magnetic nanoparticles with different lecithin concentrations. For this purpose, they first made lecithin absorb superparamagnetic nanoparticles through three steps. First, iron nanoparticles were formed by thermal decomposition of iron pentacarbonyl compound. In order to obtain magnetite particles, their mild oxidation was conducted by trimethylamine N oxide. During ultrasonication, toluene, ethyl alcohol, and distilled water were used to wash the obtained solution. The washed black powders were added in 80 ml phosphate buffered saline or PBS solution at 80 degrees Celsius to absorb lecithin. During that, ultrasonic holding time is changed from 0.5 to 1.5 hours, and the reacted lecithin concentration for dispersing particles was also changed from 0% to 50%. The colloids were centrifuged at 700 rpm for 5 minutes after they cooled the room temperature. Then, particles were dried in a vacuum and characterized by different methods. It was observed that there is change in particle size from 0% to 50% concentration of lecithin. The average size of pure magnetic particles without lecithin absorption was 9.82 nanometers, and the average particles were increased up to 12.81 nanometers in lecithin concentration of 20%. However, the distinguishable change in the particle size was not observed in the concentration of above 20%. As you can see, Figure A shows that as lecithin concentration increased from 0% to 50%, the saturation magnetization decreased from 76 to 54 nonlinearly. On the other hand, Figure B illustrates the percent weight loss with the increasing temperature for the absorbed magnetic nanoparticles with different lecithin's concentration. Roca, Costo, Rebolledo, and Ventimiglia 2009 have proposed the method of synthetic routes to produce spheroids with different sizes and shapes, which are the most suitable materials for biomedical applications. And also, Nisho, Ikeda, Gukon, Chubuchi, and Na 2007 prepared MNPs with sharply dispersed sizes ranging between 30 and 100 nanometers in aqueous solution at relatively low temperatures for about 4 to 37 degrees Celsius without any surfactant. For this purpose, sodium nitrate was added as an oxidant into a 21 millimolar aqueous sodium hydroxide solution. The rated 0.1 molar ferrous chloride aqueous solution was added to the alkaline solution, which was kept at 4, 15, 25, and 37 degrees Celsius for 24 hours. M and P's, thus synthesized, were separated from the solution with a magnet and washed several times with pure water. The morphology or size, crystal phase, and magnetization for the M and P's using TEM X-ray diffractometer and VSM respectively were investigated. As you can see in the picture, it shows that increasing the synthesis temperature from 4 degrees Celsius to 37 degrees Celsius leads to a decrease in the MNP's size and changes the MNP's shape. Furthermore, the size distribution of our synthesized MNPs becomes wide. The size distribution increases from 5.5% to 15.5%. This indicates that a higher reaction temperature accelerates both nucleation and growth of the magnetite crystals in the aqueous solution. In addition, Goodwin and his colleagues studied the single-dose toxicity effect on the treatment of doxorubicin coupled to novel magnetically targeted drug carrier. Using swine as model, they divided 18 swine into 6 groups to study the differences between without magnetic field and with magnetic field. MTC-DOX magnetically targeted drug carrier doxorubicin was injected into models to study the size-specific delivery function. By differentiating dose concentration and existence of magnetic field, they discovered that high concentration of those without magnetic field would have serious clinical signs. Otherwise, no clinical signs were observed. The picture shows clearly that the MTC particles, which are the black cluster, are accumulating around the tumor or the red part. With the help of magnetic field, they managed to release the nanoparticles around the tumor and none in circulatory system, according to toxic kinetic analysis. And we're done with the topic. Thank you for listening. I am Jolenito A. Preston Jr., BSME 4E.